So let's look at determining the rate expression from data. All right, and so we're going to just look at generic reaction A plus B makes C. We're going to run 3 experiments. Now, when you're running an experiment to determine the rate of a reaction or determine how different reactants affect the rate of reaction, you need to run experiments that hold things constant. You need to hold controls. And so if you look at this data, we've run 3 experiments, 1, 2, and 3. Now, in experiment 1, each reactant had a concentration of 0.1. Let's say this is 0.1 molar. And in experiment 2, we held the concentration of A constant because we want to only have one manipulative variable. So we held A constant and we changed the concentration to 2 to see how the rate changed. Now, we did a third experiment, but in the third experiment we held the concentration of B constant. So B was held constant and we changed the concentration of A, and we saw how the rate was affected by that change in concentration. So anytime you're looking at rate expression data and you're going to try and figure out the rate law, you need to look at finding and comparing experiments where something's held constant and one thing is changed. So we're going to look at experiment 1 and 2, and then we'll look at experiment 1 and 3 and compare those together. So in experiment 1 and 2, A is held constant. The concentration of B did what? What did B do? Well, the concentration of B doubled. But the rate was constant. The rate did not change. So how does the concentration of B affect the rate? It doesn't. B has no effect on the rate at all. We changed B's concentration and the rate didn't change at all. And so with respect to B is a zero order reactant. It doesn't affect the rate at all. By changing B, we don't do anything. So there's no effect there. Now let's look at experiment 1 and 3. So in 1 and 3 we hold B constant, so B doesn't change, but A doubled. And when we doubled A, what happened to the rate? Well, the rate also doubled. And so if we double A and the rate doubles, that means it's a first order reaction or first order reactant. And so these are the values, if you will, of the rate expression. Now the rate expression is real simple. It's just rate is equal to K times the reactants with their respective orders. Now, since B is a zero order, we don't even need to write B. We get rid of that, and we typically don't need to write the superscript 1 because it's understood. And so your rate expression for this experiment would be rate is equal to K times the concentration of A. A is the only reactant that has any bearing on the rate of the reaction. So there is your expression. All right, so here's another set of data. I'm going to pause the video, or actually I'm not going to pause, you're going to pause the video, and I want you to see if you can determine the rate expression for this set of data. So go ahead and pause the video, and when you're done, unpause and check your answer. All right, so hopefully you've done this on your own. You've at least attempted it. And so let's compare experiment 1 and 2, because in 1 and 2 we hold A constant and B changes. And so B doubles and the rate doubles. And so this reaction with respect to B is going to be a first order reaction, so B to the first, because whatever we did to B, the rate did the same thing. Now let's compare experiment 1 and 3, and B was held constant and A doubled, and the rate did not double. The rate increased by a factor of 4, and so what that means is A is going to be a second order reactant. And so the expression is rate equals K, A to the second, B to the first, or you can just write B. You don't need the first there. And so there is your rate expression for this particular reactant set of data. Now we can also work actual problems. All right, so here's some data. What's the rate if concentration of A is 0.2 molar, B is 0.4 molar, the rate constants are going to be determined to be 2.4 times 10 to the negative 3, inverse molar squared and second, given that equation, and there we've already given you the rate law. And so just plug your data in. And so the rate is equal to K, which is the 2.4 times 10 to the negative 3 inverse molar inverse second times concentration of A to the first power, so that's going to be 0.20 molar, times concentration of B squared, so 0.40 molar squared. Mathematically, that gives you 7.668 times 10 to the negative 5. Now look at your units here. We're going to have mole here, mole squared there. We have inverse mole square here, so that's going to be mole inverse second concentration per unit time, which is important for your rate unit to be correct. Okay? All right, so there's data there. Now that brings me to some point about the values or the units of K. The units of the rate constant K. Okay? And so if it is a first order reaction, overall order is first order, the unit of K is inverse second. If it's a second order reaction, the unit of K is an inverse molar, inverse second. If it's a third order overall reaction, then it's inverse molar squared, inverse second. The reason for the units of K varying is because if we have various squares and singles up here, we have different numbers of molars, and we want the n unit of rate. Remember, the rate of reaction is the change in concentration per time. We want the n rate to be moles per second. And so by giving us the proper units in the rate constant K, and then having the units cancel out in the rate expression, we'll get the rate to be in the proper units of molar per second. Okay? And so that's it for today.